Soundness proofs of abstract interpreters.
Thank you very much. So this is joint work with Kaspar Bach-Paulsen and Sebastian Erdwig. So let me first clear up some terminology in the title. Abstract interpretation is a methodology for defining sound static analysis. But why should you care about sound static analysis? So let's say you wrote a program such as this, and you want to know if this program is doing what it's supposed to be doing, namely calculating the factorial of a number. Then one way of doing this is using an interval analysis, which computes the range of numbers this program produces, giving a range for its inputs. For example, this analysis calculates that factorial always returns positive numbers for positive inputs. However, what you did not know was that this analysis is unsound. And in fact, it has just lied to you. Because when you run this program with a large number, then the factorial gets so large that it eventually overflows, and factorial returns a negative result instead, which is not in the predicted range of the analysis. So this is what can happen when your analysis is unsound. So here are some other use cases in which soundness of static analysis is really important. A type checker, for example, is a specific kind of a static analysis. And if a type checker is unsound, it misses type errors that can occur at runtime, which leads to less stable programs. Or an information flow analysis, for example, computes if unsanitized user input can reach sensitive code in your application. And if this analysis is unsound, this might lead to security problems. Or a compiler optimization, for example, that is based on unsound static information might change the semantics of your program, which can lead to really unexpected behavior. So in all of these cases, ensuring that the static analysis that you use, that this analysis is sound, is really important. But what does it take for an analysis developer to prove that their static analysis is sound? Well, let's look at an example. By the way, all the code that I show you in these slides is Haskell code. So let's say we want to implement a static analysis for the language construct if0. So let's look at the concrete semantics of if0 first. So if0 implements a conditional, so we first evaluate the condition e1, and based on the resulting value, if the resulting value is 0, we first evaluate the first branch e2, and otherwise we evaluate the second branch e3. So now let's implement an interval analysis for this language construct in form of an abstract interpreter. And so this abstract interpreter basically is like a regular interpreter. However, it produces intervals as values instead of numbers. And we get code that looks like this. So what we do is we also evaluate first the condition, and then we check if the resulting interval is exactly the interval 0, in which case we evaluate e2. In case the interval does not contain 0, we evaluate e3. And in case the interval contains 0 and other numbers, we have to over-approximate, evaluate both branches, and join their results. Now, in the soundness proof of this analysis, what we have to do is we have to relate outcomes of the abstract interpreter to outcomes of the concrete interpreter. We have to figure out how they relate. And we end up with a relationship like this, where, for example, the last case relates to both cases of the concrete interpreter. So for if0, this proof was simple enough. But let's look at the slight variation of if0, and let's see what happens. So this variation is called try0, and try0, in addition to checking that the condition evaluates to 0, also checks if the condition fails to evaluate. And in case the condition failed to evaluate, we also evaluate e3. So let's now look at the abstract semantics for try0. And we get code that looks like this. And I don't expect that you read all of this code, just observe that it has to distinguish 7 cases. Now again, in the soundness proof, we have to figure out how the cases of the abstract interpreter relate to cases of the concrete interpreter, and we end up with a relationship like this. And the problem with this kind of proof structure is these proofs are really entangled, which means that it's really hard to decompose the soundness proof of try0 into smaller lemmas, which are easier to prove. And this is the exact problem that we tackle with our work. Our work makes the soundness proofs of abstract interpreters compositional. So let me tell you a little bit how this works. So I've shown you examples of concrete interpreters and abstract interpreters. And you might have observed that, sure, these interpreters are different because they operate on different values, for example, but also they are quite similar because they recurse over the same expressions. And so what we have observed is that it's often possible to make these similarities between concrete and abstract interpreter explicit in something which we call a shared semantics or a shared interpreter. More specifically, this shared interpreter is composed of a number of primitive language operations. And the types of these language primitive operations is captured by some kind of interface. We can then instantiate this interface with two different instances, one concrete instance and one abstract instance. And when we then instantiate the shared interpreter with, for example, the concrete instance, we end up with the concrete interpreter that we are interested in. So what have we gained from this restructuring of the concrete and abstract interpreter? Well, now we describe the interpreters by their components instead of monolithic interpreters. And what we gain is that now for each of these language primitive operations, we can prove one separate Soundness lemma. So let's see how this works more concretely at the example of try zero from before. Of course, the idea of try zero is to capture the semantics of try zero with two operations. One is called try, which checks if something has failed to evaluate, and if zero, which checks if the number is zero or not. Then we can write two instances with two operations each, and then prove two separate soundness lemmas whose proof structures I've written on these arrows here. So when we compare these two proofs now to the original proofs of the conventional abstract interpreter, then these proofs are a lot simpler because, first of all, we have less abstract cases to distinguish in these proofs. And furthermore, each abstract case relates to less cases of the concrete interpreter. So I hope this convinces you that these proofs are simpler than the original proof. So let's say now we are in a position where we have actually proven these instances sound. So we have proven one soundness lemma for each of the operations. Are we done now? No, not quite. What we actually want to know is if we can take these soundness lemmas and compose their proof into a proof of the entire analysis. This is what we actually want to know, is the complete analysis sound. But this is not quite obvious why this should work. And in fact, it depends on the meta-language with which we describe these shared interpreter and its interface. And furthermore, it depends if this meta-language comes with a suitable reasoning principle that lets us compose this proof. So in these slides, in this analogy, I've used Lego bricks as a meta-language. But of course, Lego bricks don't allow us to describe computations. So in our work, we've looked at arrows known in Haskell as a suitable meta-language. So what are arrows? Well, arrows allow you to capture the effects of your programming language. So let's say you have an interpreter that has this type, then we can capture the effects of this language with an arrow type interp that looks like this. And this arrow type captures the effects of passing of the environment and propagation of failure. And furthermore, it also takes two type parameters. It takes one type parameter A, which captures the inputs of this computation, and a type parameter B, which explains the outputs of this computation. And with this arrow type, we can then describe the type of our interpreter itself with interp x per val, which means it's a computation which consumes expressions and it produces values. Furthermore, we can describe the code of the interpreter itself with a pretty notation which is built in GHC. And this pretty notation looks very similar to monetic do notation. However, under the hood, this pretty notation desugars to a first-order language, which consists of a number of arrow operators and user-defined operations such as plus in this example. And the specific property of this language is it's a first-order language, which means we get a suitable reasoning principle, namely an induction principle. So let me tell you how this induction principle now helps us to compose a soundness proof. So each premise of this induction principle above the line becomes one soundness lemma for the instances that we have to prove. And what the induction principle guarantees is that all arrow code based on these operations also has to be sound, including the shared interpreter that we are interested in. So this induction principle effectively composes the proof for us. Once we've proven that the instances are sound, there is no more proof work to be done. However, you might have observed that this induction principle has one Achilles heel, which is this premise right here. It says that all pure functions which occur in the shared interpreter, which are embedded with the arrow operator R inside of an effectful arrow computation, also have to be sound. The problem with this premise is this is a lot of additional proof work, which is also totally boring, because these functions do the same thing in the concrete interpreter and in the abstract interpreter anyways. So why should they be unsound? So let's look at an example of such a function. Maybe we can do something about this. So let's say f is such a function, and it's a function that takes a list of values and it maybe returns one of these values. And furthermore, this function is parametric in the value type because the concrete interpreter and the abstract interpreter use different value representations. Now, what we can learn from this only by looking at this type is that this function can choose an element from this list solely based on the length of the list, not on the contents of the list, because it's universally quantified in the contents of the list. So for example, when we call this function with a list of numbers 1, 2, 3, then it might choose the second element. And when we then call the function with a list of parities of the same length, odd, even odd, then it also has to choose the second element. And furthermore, what we can learn from this type is, if each element of these lists was related with, for example, an abstraction function that for each number returns its parity, then the output also has to be related by the same abstraction function. And this is exactly what we need to prove that this function is sound. And that this holds is guaranteed by a very powerful reasoning principle called the abstraction theorem, and it holds in languages which enjoy parametricity. And this abstraction theorem now gives us an entirely second way to compose the soundness proof for us, to a soundness proof, the complete analysis. So this means now we have actually two meta-languages and two reasoning principles that compose the proof for us. So how do they compare? So arrows on the one hand have the benefits that they can be embedded in an existing meta-language, such as Haskell, Scala, or Java, for example. Whereas when we want to use the abstraction theorem of parametricity, this is rather restricted because we have to choose a meta-language which enjoys parametricity. And not very many languages these days have this property. However, I've shown you that arrows have slightly more proof work because we have these pure functions to prove sound, where these functions in the case of parametricity come as a free theorem. So we don't have to prove them, so which means that the second technique means less proof work. So we've evaluated our technique by building two analyses with this technique. We have created a tree shape analysis for a program transformation language called Stratego, and we have created a standard control flow analysis for PCF, a higher order function language with functions. Now, in both cases, we were able to decompose the soundness proof into smaller lemmas, which can be proven individually, and soundness of the complete analysis comes by composition. And in our paper, I invite you to take a look in our paper where in more detail we discuss the effort and the complexity of these soundness proofs. So to summarize, in this talk I've shown you a problem with the soundness proofs of conventional abstract interpreters. Namely, that's really hard to decompose these soundness proofs. I've then shown you a way to restructure the interpreters such that we can prove smaller soundness lemmas for the language primitive operations. And then I've shown you a way, two different ways, to compose the soundness proof from soundness of these instances into a soundness proof of the complete analysis. And all the code of our case studies is open source and is available at this URL. This is all I have. Thank you very much.
Thank you. So, a question is if these techniques that you describe can be used, can be translated to a monadic setting.
To a?
Monadic setting.
Right. Very good question. So actually I'm prepared for this question. Excellent question. So the problem with monads is monads are a higher order language, which means that their bind operator has this functional there. And then it really depends on the meta language that you're using if you get such a principle, reasoning principle, that lets us compose the soundness proof. So for example, let's say for the sake of the argument, we would choose Java as a meta language. Then we would have to figure out a way how to compose the soundness proof along all Java statements. That might be very difficult. However, if your meta language that you use is System F and you use monads in this kind of setting, this would work. Yes.
Okay. So I guess on the same line, it's Alessandro Russo asks, did you try it with monads or other structures? And how critical was to have the control flow explicit and known, one of the features that arrows provide to make this work?
Sorry, I don't understand this question.
Did you try it with monads or other structures? And how critical was it to have the control flow explicit and known? Because like arrows give you explicit control flow. So how critical was this property of arrows to make your proof work?
Right. So in our experiments, we have used arrows only. We haven't used monads. And so the use of arrows wasn't really restrictive in this sense. Yes. So yeah, maybe we should take this question offline and.
Okay, and the last question by Jenny Hackett is, can arrow induction and parametricity be combined?
Yes. So so when you use arrows in a meta language which enjoys parametricity, then you can combine the ways of arrows that allow you to capture the effects of your programming language and still get the benefits that these pure functions come as free theorems. Yes.
Okay, thank you very much.
Thank you.